Good evening. I'm having some microphone issues, so it's to the headset for this video. But this one is going to be a little more advanced in concept, not in mathematics, but in concept. And I want to talk about cooling systems, more specifically, what we're doing with a cooling system in a car and what is reversed cooling. So some of us are old enough to remember this small block Chevy and how it was the staple, or still technically could be called the staple of classic car high performance. It's the universal power plant that a lot of people put in frick and everything. And it's a decent platform. You can do a lot with it, but it has a lot of limitations. After the small block Chevy came the LT1 series. And the LT1 series, they had realized and learned some things, and they were able to make some significant gains in power density and ease of making power on it. But it didn't really get as popular, I think, as it probably deserved to be due to the complexities of the fuel injection systems that also came out at the same time with the LT1. So the 80s and 90s, late 80s, early 90s was when fuel injection was really starting to take off. Electronic fuel injection, that is, really starting to take off. However, it was really complicated. Um, Due to limitations in the solid state circuitry and types of solenoids and actuators and that kind of thing. A lot of stuff was done with vacuum lines and diaphragms, and so these cars had just nests of hoses under the bonnet there. So it was just hose after hose after hose, and lots of extraneous systems to try and tackle certain tasks. Whereas now modern fuel injection, especially on the Subaru, is quite simple. There's not nearly as many hoses. There's some wires, but overall the systems are um, they're very streamlined and efficient at operating. So later on came the LS, and they did some more stuff. And theory is they copied some Ford parts. I guess the head design and things like that is something that I hear a lot of. But overall, the LS makes way more power than a small block Chevy does, and it it gains more power for the same modification than a small block Chevy would. But it really all started with the LT. So, what was one of those things that they figured out? One of those is cooling, and known as reverse cooling. And reverse cooling, I don't know why they call it reverse. I know they call it reverse. They call it reverse because originally the cooling systems would pump water into the cylinder block to pull heat from the cylinders, and then the coolant would flow up through the head and get distributed there. And so that was conventional cooling. And so when they realized, holy crap, if we cool the heads first and keep them cooler, then we can get more power, we can run higher compression ratios, we have less knock tendencies, all this stuff happens that's really advantageous for us. And so they called it reverse cooling, because now it was going from the heads to the block. So why did that work? Right? What about that worked? And so what I want to do is I'm going to share with you a few things that talk about how that works and why that works. So first off, if you think about cylinder pressure, cylinder pressure is the highest when the piston is really close to top dead center. And if we look at this pressure trace, what we'll see is that the cylinder pressure in a combustion engine is the highest right around 20 degrees after top dead center if we properly advance it. So if you look at that graph I posted there, 50-degree advance has peak pressure at top dead center, and that's actually bad in that situation. That's too much pressure at the top, and you're not gaining anything by doing so. At the 30-degree mark there, that is the correct ignition advance for this engine, and you'll see that the cylinder pressure peaks around 20 degrees after top dead center. And you'll also notice though that the 50 degree has more peak pressure, but if you look at the graph to the right of that, you'll see that the torque actually does not go up with that. It's just you're wasting energy and you're adding heat And heat is the thing that we're really concerned about at this point, right? We're talking about pulling heat out of the engine. And so how much heat is there in the engine, and where is it concentrated the most? Well, it's concentrated the most in the combustion chamber. And I don't have modern equipment to prove that to you, but I do have some entries out of this book here, Internal Combustion Engine Fundamentals by John B. Haywood. And then I have this graph here, and reading this and putting that graph together, we can figure out together where all the heat is. And so in this section is actually about combustion chamber temperature. Hey, look at that. It says that the surface area of the combustion chamber varies through the cycle. Okay, the heat flux into the containing walls changes continuously. And so from small negative value during the intake process. So what they're saying here is they're calling, in this case, the combustion chambers the entire volume at this point is what they're calling it. So during the intake process, the piston is moving downward, and so the heat flux is actually reversed. It's actually cooling at this point, which is expected, right? You expect that when the intake air comes in, it's going to cool whatever's in there. So it says the heat flux in the container walls change from a small negative value during the intake process to a positive value of order several megawatts per square meter early in the expansion process. Well, if we look at our graph, we can see where early in the expansion process is, knowing that our ignition event is at 30, and we can see that expansion starts to move up after that. Now, how early is it? I mean, I don't know how early they're talking, but if you were to look at the piston location at 30 degrees before top dead center versus 20 after, the piston does not move much. You know, as the piston is approaching top dead center and the rod swings over the top, right? There's a lot of degrees of crankshaft rotation with hardly any movement at the top of the rod, which means the piston is hardly getting much closer. So the piston goes really fast through 90 degrees, and then it slows down, it goes through top dead center, and then it comes back down again. I'm going out of screen on my camera there, sorry about that, but I think you can get the idea. And so what that's telling us is that the majority of the heat, or at least the highest rate of heat transfer into the engine during the combustion process, is early, and that means that's when the piston's at the top. So where is the majority of the heat going to be? Well, it's going to be when the piston's at the top. Most of the combustion happens when the piston is at the top. Most of the energy formed happens when the piston is near the top. So anywhere from 20 before to 20 after, we'll just generalize that in this case. Well, it's all at the top. So what does that mean? Well, that means that if we need to remove the heat from the head, put some priority on that, then we can reduce combustion chamber temperatures, and we can reduce our knock tendencies and things like that. Now, why am I bringing that up? Well, I'm bringing that up because the EJ has a tendency to break the number 4 piston. Some of that is by design from Subaru as far as the programming is concerned, and some of that is just because of the mechanical system itself. So in the EJ, the knock sensor is really close to cylinder 4, but it is it's in that picture. Well, it's not in that picture, but next to bolt T1 there. Let's see if I can point to it. Wah! Right, that little bung area, that's where the knock sensor sits, okay? Cylinder 4 is right there, cylinder 2 is right there. All right, so the knock sensor sits really close to cylinder 4. That means the knock sensor hears cylinder 4 better than anything else. Cylinder 3 and cylinder 2, or cylinder 1, are really far from that sensor. And not only are they far from that sensor, but the block is split, and there's silicone between the two halves. Now, how well does sound transfer through a solid material? I mean, pretty well. It conducts very well. But then if you split that material and you put it together, well, you lose some of that transfer. You lose a significant amount of it. Then you add silicone between those two halves, and how much are you going to hear? You're going to hear a lot less. Are you going to carry sound? Sure, yes. You're absolutely going to hear it. And then in addition to that, the valve train for cylinder 4 is really close to that sensor. The valve train for cylinder 4 is closer to the sensor than the combustion in cylinder 3. Especially the combustion in cylinder 1 and the combustion in cylinder 2. And so when you're listening for a knock event, which usually happens around 20 degrees after top dead centers, where knock events usually happen because they usually happen near peak pressure, you're also having valve events happen on other cylinders. If you look at some cam profiles, you see that some cams don't close the exhaust valve until you're 20 degrees after, or so many degrees after. And if you have exhaust ABCS, and you retard the exhaust cam, you're pushing it over the closing point to over top dead center. And so you're going to have valve events at the same time when you would or could be having knock events. And so Subaru realized that they're having these issues hearing all 4 cylinders and not being able to filter out the valve events from the other cylinder because those noises are really close to that sensor, closer than the combustion in the other chambers. And in the FA, you can see that they addressed it in the FA because they added 2 knock sensors. Well, they added 1 knock sensor for a total of 2 knock sensors, 1 on each case half. And they put them closer to the cylinders than to the heads. So they were addressing that issue with that. Well, so what did they do with EJ though, right? They still stuck us with 1 sensor, and they never threw a second one in there. Well, they said, okay, we can hear cylinder 4. And we know that if we make cylinder 4 the most aggressive cylinder, we throw extra timing at it, we pull fuel out of it, right? If we make the most aggressive cylinder and we keep it knock free, then the other cylinders would have to be knock free because they're not nearly as aggressive. And that's what they did. You look at any of their calibrations and you can see cylinder 4 has more timing, or the other ones have less based on what the calibration has positive in cylinder 4 or negative in 1, 3, and 2, or whatever. And then the fueling, typically cylinder 4 has less fuel as well. Well, there's another thing, and this occurred to me when I was taking the engine apart. Cylinder 4 also has less cooling. The head has less cooling. Now, if you look at the picture that's behind me, I'm going to move my head out of the way, wrong way. You'll see the water pump there bolts to the front of the block itself. It is near the head, but it bolts to the block, and it discharges water through the crossover to the side, but also through the block case itself, and then into the head. And while Subaru shows a flow path, I'll bring this up for you, this coolant flow path here, and they show it moving from, if you look at the number 14 is the water pump. It's on the left side there. And then you have it flowing into 12, which is the block, and then it shows 12 to 13 to the head. It has these 4 ports showing the head, and that's just the holes drilled in the in the deck of the head gasket and the head. The deck is actually mostly open on these things anyways nowadays. So it moves through those ports in the head, and then it shows this little crossover tube over there. Well, there really isn't a crossover tube. If you look at the cooling system on this thing, there really isn't a crossover tube, and it shows this little flow path here. It's a little weak, like and the flow path kind of bypasses the exhaust side of cylinder 4. And if you look at a cylinder 4 piston that has failed from knock, you see that almost every time the part that breaks is the exhaust side of the piston on cylinder 4. So when I look at this, I say, it seems to me that not only is cylinder 4 the most aggressive in tuning, but it's also most aggressive in lack of cooling. If you look at that picture some more, you'll see the passenger side head or right-hand side head. It goes from number 9, which is again the block, to 8, which is the head, and then to 7, which is the turbo. And the turbo is fed out of the head. And then it goes through the turbo, the reservoir, and then back to the inlet of the pump again. So the passenger side head has a flow path that flows through the head, promotes flow through the head to the end of the water pump. But 4 doesn't have that. Now the twin turbo Subarus do. The twin turbo Subarus, they have a coolant line that comes out of the head and feeds the turbo, and then goes to the crossover tank and that kind of stuff. And so there's a forced flow path on the driver's side head, and that helps to aid in cooling. So my newest product that I have produced is addressing that exact issue. And so my goal is to increase the flow around cylinder 4, the passenger side, the driver's side head, and by doing so, make it not so aggressive on cooling. I want to bring it down. I want to reduce the knock tendency of cylinder 4. And if I can increase the cooling to cylinder 4, I believe that I can do that. I've already proved that I can get more cooling to it. Now I need to somehow quantify the power output, right? And that's going to be really hard to do. And like some mods, you just got to kind of go, well, I can see that that's supposed to work, and then go for it. So I have been working on this for quite some time. I'm excited to when I actually reveal what it is and how it works to everybody. Just want to make a video, talk about reverse cooling a little bit, which I did, the cooling systems a little bit, which I did, and then as to why it is my newest product, improves the cooling of cylinder 4. And I may even be doing some internal work or specialized head gasket to help promote flow to cylinder 4, or at least to change the order in which the cylinders are fed, um, and to help get better cooling balance. But I have some more RTDs to install and other things to work out to figure that part out. But the initial products come out in just a few weeks. I look forward to hitting the market. I know it's going to help, and I am just happy to be able to bring something new to the market that addresses a problem that some people didn't realize existed, but it's something that I've been trying to really work on for quite some time. So I'm really excited, and I hope you guys are too. And that's it. If you have any questions about the reverse cooling, or anything about the Subarus, the product, or anything else, you want another video, please feel free to shoot me a message. Dominic at Getadomtune.com. You can go to Getadomtune.com. If you can't remember my email address, you can hit up the Facebook page. You can call us on the new number. I say us, it's just me. I rarely ever answer though, because I still have lots of stuff going on. So you can text, but again, the best way is email. You can comment on this video here, like, subscribe, whatever, share it with your friends. I appreciate all of it. I love you guys, and I hope this taught you something about Subarus and V8s even.